In continuation of the Arrhenius equation that I have uploaded in my last lecture, today I like to show you some apparent deviations of this Arrhenius equations and its some related problem, and it is lecture number 11. You see, reactions are of two types generally. One is simple, elementary, one step, and other is complex or multi-step. And generally, in multi-step reactions, some observations show that the rate constant decreases with the rise in temperature, which is against the prediction of this Arrhenius equation. There are so many complex reactions of this type, but I will show only one example to demonstrate how the deviations of Arrhenius equation could be explained. And this apparent deviation suppose one reaction is oxidation of nitric oxide, twice NO plus oxygen and giving twice NO2 and rate constant K. And for this reaction, it is a complex reaction. It consists of several steps. And for this reaction, the rate constant K is decreased with rise in temperature. So, in order to explain this abnormal or apparent abnormal behavior of this equation, let us see what is the mechanism of this reaction. Mechanism means the detailed description of the paths by which the reactants will undergo to the products. So, the mechanism of this reaction is that twice NO sign of reversibility equal to N2O2 and it is equilibrium constant K, and this rapid equilibrium is settled, and this is equation number 1. So, this is the intermediate compound. Next step, N2O2 plus oxygen and the rate constant K2 and giving you twice NO2, and it is slow, and equation number 2. And we know that in a rate process, in multi-step reactions, slowest step is the rate determining step. So, rate of this reaction we can write in terms of this product d NO2 and dt. It is the rate of this reaction in terms of this product. Here 2 will come up half, and this is equal to, according to this mechanism, we can also derive or formulate the expressions of the rate constant by the use of the suggested mechanism. If the suggested mechanism give you the exact value of k, then the suggested mechanism is found to be correct. So this one K2 and concentration of N2O2 and concentration of oxygen. But from equation 1, equilibrium constant is equal to N2O2 divided by NO square, or concentration of N2O2 equal to Ke, equilibrium constant, and concentration of NO and square. So this intermediate concentration of this intermediate compound can be obtained from this equation, from this step 1. So if we substitute this one, then it will be K2 and Ke and concentration of NO square and concentration of oxygen. So this is found to be, these two are constant, and product of the two constant will give you a new constant, and this you can write this K. This you can write this K into NO square and O2. This according to the suggested mechanism, it is seen that second order with respect to NO and first order with respect to oxygen, and experimentally it is also exactly the same. So suggested mechanism is found to be correct. This K, the observed rate constant, K equal to K2 and Ke. K2 and Ke. So you see, rate constant is observed rate constant, and it could be determined experimentally. If we measure the rate constant of this reaction at two different temperatures, then it is found that this, with the rise of temperature, this rate constant of this reaction is found to decrease. How could you explain? This could be explained on the basis of this mechanism. You know, it is the rate constant. K2 is the rate constant, so it behaves normally according to this Arrhenius equation. So when T is increased, K2 also increase. But this equilibrium constant, it is the equilibrium constant of this dimerization reaction, and in this dimerization reaction new bond is formed. So new bond is formed means energy is released. So this reaction is exothermic. This reaction is exothermic. Exothermic means del E equal to negative. We can recall the Vent of equation. We can recall this Vent of equation. Vent of equation, which relates this equilibrium constant with this temperature. So it is d ln Ke divided by dt equal to del E by RT square. Since del E is negative, so this one is negative, rest these two are positive, so whole left right hand side is negative. This right hand side negative means with the rise of T, Ke is decreased. So with the rise of T, equilibrium constant is decreased, and the equilibrium constant, decrease of equilibrium constant is so much or so large that it overcomes the increase of this rate constant to this increase of temperature. So as a net result, the total these two found to decrease with rise in temperature. This is the explanation. Now I show you some problems. These problems I have chosen. These problems I have chosen from the different examinations, which are very important and notably different from one to other. So I will show you 4 problems. Problem number 1. Problem number 1. The rate constant of a reaction is found to increase by 2% with the rise of temperature by 0.1 degree centigrade at 25 degree centigrade. And our task is to calculate the activation energy. Calculate the activation energy of this reaction. Activation energy of the reaction. It is set in central selection examination, and it is the (1996). So how could you solve this problem in a most easiest way? We have the Arrhenius equation. You may see, you can remember there are 4 different forms of this Arrhenius equations, and one important relation is d ln K by dt equal to activation energy divided by RT square. It is one form, differential form of this Arrhenius equation. we can do it, say it is dk by k divided by dt equal to EA by RT square. So activation energy which we have to calculate, this activation energy equal to RT square into dk by k divided by dt. Now let us put the data given in this problem. Here R equal to 8.314 into 10 to the power minus 3 kilojoule mole inverse, Kelvin inverse, and temperature 25 degrees centigrade. 25 degrees centigrade means 298 Kelvin. So it is 298 Kelvin square into this dk by k, it is 2%. 2% means its value is 0.02. So numerator is 0.02 and dt is 0.1 degree, 0.1 degree centigrade, and you know the difference of temperature in centigrade and the Kelvin are same. So you can write instead of centigrade scale, we write this Kelvin scale. Now if we solve, say this and this cancels, and this one all the k unit are totally cancelled. Now if we solve this problem, then the calculation will give you 147.6 kilojoule mole inverse. This is the activation energy. Now we are coming to this problem number 2. Problem number 2. The rate constant is found 1.5 into 10 to the power 7 second inverse at 50 degree centigrade, and 4.5 into 10 to the power 7 second inverse at 100 degrees centigrade. Calculate the Arrhenius parameter E and A of the reaction, of this reaction. This is also a second problem relating to the Arrhenius equation. So in this case, at this 2 temperature Arrhenius equation, the solution will be is the ln K2 by K1 equal to EA by R and T2 minus T1 divided by T1 T2, and this is the another form of the Arrhenius equation, which is the rate constant at two different temperatures. So first we find out the activation energy. Putting the values here, ln K2 is 4.5 into 10 to the power 7 second inverse divided by 1.5 into 10 to the power 7 second inverse. These are the values of K2 and K1 equal to EA divided by R equal to 8.314 into 10 to the power minus 3 kilojoule mole inverse Kelvin inverse, and here temperature difference 100 minus 50 in centigrade, and so it is also 50 Kelvin, and the denominator 50 degrees centigrade equal to 273 plus 50 equal to 3 2 and 3 Kelvin. So it is the, and 100 degrees centigrade equal to 273 plus 100 equal to 373 Kelvin. So let us put here 323 Kelvin and 373 Kelvin bracket close. So this one or this cancels, second inverse cancel, so it is only 3 ln 3 equal to EA divided by 8.314 into 10 to the power minus 3 kilojoule mole inverse Kelvin inverse, and you see one Kelvin and another Kelvin cancels, and Kelvin inverse and this Kelvin cancels, so it is into 50 divided by 327 into 373. If you do the calculations for this activation energy, approximately 22 kilojoule mole inverse, only the value. Now the second parameter. For the calculations of the second parameter, let us find another Arrhenius relations. K equal to A into e to the power minus EA by RT, or A equal to K into e to the power EA by RT. If we put these values, then say at 25 degrees centigrade, we can use any temperature data for at any temperature as the at 50 degrees centigrade, as the at the Arrhenius factor A is independent of temperature as assumed. So equal to 1.5 into 10 to the power 7, and it is second inverse, into e to the power activation energy equal to 22 kilojoule mole inverse divided by temperature R equal to 8.31 kilojoule, 8.31 into 10 to the power minus 3 kilojoule mole inverse and temperature is 323 Kelvin. Kilojoule mole Kelvin inverse. So Kelvin inverse, Kelvin cancelled, kilojoule mole inverse, kilojoule mole inverse. So it is equal to 1.5 into 10 to the power 7 second inverse, and this value whenever you calculate, its value will give you 3613. 3613. So total value is coming up 5.4 into 10 to the power 10 second inverse. So both these Arrhenius constants are calculated by using this data giving in this problem. Then problem number 3. Though we have assumed the activation energy is independent of temperature, but in many cases it is found to be dependent on temperature. So one such type of example, say problem number 3. Problem number 3. This problem number 3 is the state Arrhenius equation. Arrhenius equation which depends on showing the variation of rate constant with temperature. The next question is that express the energy of expression. Express the energy of activation energy of activation in terms of C for the relation K equal to B root over T and 10 to the power minus C by T. You have to find out the activation energy in terms of C. This is also very important. It has been set in Bardwan University in 1999. So since it is 10 base, taking this log 10 base, K equal to 10 base B plus half log 10 T minus C by T. If we convert this natural logarithm, then natural logarithm ln x equal to ln base E equal to 2.303 log x. So if we multiply 2.303 both sides, then it will give you ln k equal to ln b plus half ln t and minus 2.303 C by T. Now you can differentiate with all the terms are in natural log. So you can differentiate with respect to temperature. It is d ln k divided by dt. This is constant 0, and here it is with respect to T 1 by 2T and minus here 1 by T, differentiating with respect to T, it becomes plus 2.303 C by T square, and this is equal to T square, and here 2.303 C plus a half T. If we now write this Arrhenius equation, Arrhenius equation is the d ln k by dt equal to EA by R T square. So d ln k by dt, left hand side same. So this one is equal to this value. So whenever we equate this one equal to EA by RT square equal to 2.303 half plus half T, 303 C plus a half T divided by T square. T square cancelled. So activation energy equal to 2.303 RC plus half RT. So this is the expression of activation energy in terms of the C. This is the expression of activation energy of this reaction in terms of C. Then another last problem 4. Last problem 4. For two parallel reactions A, B to C. Here it is path 1, K1, rate constant, activation energy is E1. Here it is K2 and activation energy E2. And we have to show the overall so that the activation energy of activation energy E for disappearance of disappearance of A is given by given in terms of E1 and E2 for two paths. E equal to K1 E1 plus K2 E2 divided by K1 plus K2. This is to be shown for these two parallel reactions. E is the activation energy for the disappearance of A, and E1 is the activation energy for the step A to B, and E2 is the activation energy for this A to C, K1, K2, their respective rate constant. So we have to show this relation, and you know the Arrhenius equation dk1 by dt ln k1 by dt equal to E1 by RT square, or we can write this one dk 1 by k and dt equal to E1 by RT square. So dk1 by dt equal to k1 E1 by RT square. Similarly, for A to C path, or this reaction, it will be d ln k, it will be dk2 divided by dt equal to k2 E2 divided by RT square. If we add this 2, then it is d k1 plus k2 by dt, k1 by k2 by dt equal to k1 E1 plus k2 E2 divided by if we add these two divided by RT square. But for overall disappearance of A, let this rate constant is K for disappearance of A, and E is its activation energy. Then in this case also d k divided by dt equal to k E divided by RT square. So equating both sides, it could also be written as, we know the K equal to K1 plus K2 for two parallel reactions. So instead of writing K, we can write K1 plus K2. So d K1 plus K2 divided by dt equal to instead of k, k1 plus k2 into E divided by RT square. So equating this one, and this one, if we equate these two, then left hand side same, right hand side also same. So we are having this k1 plus k2 and E equal to k1 E1 plus k2 E2, or E activation energy for this disappearance of A equal to k1 E1 plus k2 E2 divided by k1 plus k2. So this has been shown here. So this is all about the apparent deviation of this Arrhenius equation and some very important related problems of this Arrhenius equations. So this is all about this lecture number 11, and I hope you can understand, and thank you for you all for watching my video. Okay.